Welcome to this explainer. Today we're jumping right into Module 6 of Cybersecurity and Ethical Hacking to decode the ultimate blueprint of digital communication. We're literally going to look under the hood of the internet itself and figure out how data actually gets from point A to point B. Okay, let's dive into this. Before we get into the heavy technical weeds of network engineering, we really have to answer a fundamental question. How does a simple click safely cross a chaotic globe? Think about it for a second. We've got billions of devices out there, smartphones, laptops, massive servers. They're all made by different manufacturers running entirely different operating systems, and they're communicating over fiber optics, copper wires, and invisible Wi-Fi signals. Yet they seamlessly talk to each other in milliseconds. How is that level of coordination even possible? Well, here is our roadmap to figure that out. First, we'll look at the internet's invisible architecture. 2, the OSI 7-layer model. 3, the practical TCP IP suite. 4, data encapsulation and decapsulation. And finally, 5, packet sniffing with Wireshark. Starting off with Section 1, the internet's invisible architecture. So the crucial point to understand right out of the gate is that the Open Systems Interconnection, or OSI model, isn't a piece of software you just install. It's actually a 7-layer theoretical standard for network communications created by the ISO. It breaks down the incredibly complex process of networking into 7 distinct, highly manageable functional layers. By giving each layer a very specific job, it standardizes everything, which promotes compatibility between completely different systems and makes troubleshooting infinitely easier for us. Which brings us nicely to Section 2, the OSI 7-layer model. To really grasp this without drowning in acronyms, think of it like sending a physical package in the mail. Layer 7 is you writing the actual letter. Layer 6 is formatting it so it's readable. Layer 5 is calling the recipient to agree on how you're going to communicate. Layer 4 is choosing a reliable delivery service. Layer 3 is the postal service determining the best geographic route. Layer 2 is your local post office sorting it. And all the way down at Layer 1, well, that's the actual physical postman driving the truck to make the delivery. Now notice how the top 3 layers handle your software and data format. Layer 7, the application layer, is your direct interface, like your web browser using HTTP or your email client using SMTP. Layer 6, the presentation layer, takes that data and handles the formatting, the compression, and crucial security tasks like encryption and decryption via TLS and SSL. Then Layer 5, the session layer, acts as the dialogue manager, keeping that connection between devices organized and open. Because these top layers manage user-level software and data, this is exactly where hackers target things like HTTP floods or SSL stripping. Moving down to the hardware, layers 4 through 1 handle the actual transit, making them the absolute battleground for network-level attacks. Layer 4, the transport layer, ensures end-to-end delivery using reliable TCP or fast UDP protocols. Layer 3, the network layer, assigns logical IP addresses and routes those packets across the globe. Layer 2, the data link layer, manages local node-to-node transfer using physical MAC addresses. And finally, Layer 1, the physical layer, translates everything into raw bit streams, just pure zeros and ones sent over cables or Wi-Fi. If you want to understand attacks like IP spoofing, or use a tool like Ping to test Layer 3 connectivity, or check your ARP table to see Layer 2 bindings, you have to master these layers. All right, Section 3, the practical TCP IP suite. While the OSI model is a fantastic theoretical guide, the TCP IP suite is the practical 4-layer model that's actually implemented globally. The real world basically simplifies the theory. TCP/IP condenses the top 3 OSI layers, application, presentation, and session, into one unified application layer. The transport layer remains exactly the same. OSI's network layer becomes the internet layer in TCP/IP. And finally, OSI's data link and physical layers get mashed together into a single network access layer. It's the exact same concepts, just a much more streamlined architecture that powers the internet today. Let's move on to Section 4, data encapsulation and decapsulation. So how does a raw piece of data actually get packaged for this crazy journey? Well, this is the top-down encapsulation process. Imagine your data getting wrapped in a series of digital envelopes rapidly as it moves down. Your raw application data gets passed to the transport layer, which slaps on a TCP or UDP header, transforming it into a segment. Next, the network layer wraps that segment in a source and destination IP header, creating a packet. Then the data link layer adds a MAC address header and trailer, turning it into a frame. Finally, the physical layer converts that frame into raw bits to be shot across the wire as signal. And when those bits reach their destination, the receiving device performs the exact reverse pipeline, which we call decapsulation. The receiving machine takes those bits and rebuilds the frame. It checks the MAC address at layer 2, strips that header off, and passes the packet up. It checks the IP address at layer 3, strips that header, passes the segment up. It literally just keeps stripping away headers layer by layer until the pure original application data is finally revealed to the end user. Okay, section 5, packet sniffing with Wireshark. Now that we know the theory, it's time to bring this into the cyber lab and look at the actual matrix of data. To observe these abstract models in action, we use Wireshark. It's a free network protocol analyzer that captures traffic and decodes it, allowing you to see those encapsulation mechanics happening in real time. Whether you're an IT professional troubleshooting a slow network or an ethical hacker hunting for clear text passwords, Wireshark is the absolute industry standard tool for packet analysis. Let's look at a quick 3-step practical blueprint for this. First, environment setup. You install Wireshark and identify your active network interface using a command like IPA in your terminal. Second, capture execution. Start the capture and generate some live traffic, like using the curl command to request a basic website. Third, and this is the best part, encapsulation analysis. You stop the capture and inspect the layer 2 Ethernet frames, layer 3 IP headers, layer 4 TCP ports, and layer 7 HTTP payloads right there on your screen. Now, to avoid getting overwhelmed by background noise in Wireshark, because let's face it, your computer is talking to hundreds of things in the background at any given second. Use this beginner workflow. First, go to statistics, then conversations. This gives you a bird's eye view of exactly who is talking to who. Second, find an IP address that looks interesting. Right-click it and select Apply as Filter to isolate just that traffic. Third, right-click a specific packet and hit Follow Stream. This magically pieces all the segments back together so you can read the exact conversation as it happened. We can also slice through the network chaos using display filters. For example, simply typing HTTP spots unencrypted web data, which is a massive security risk. TCP.port equals 443 zeroes in on secure HTTPS traffic. If you're using terminal tools like Netstat to monitor active socket connections, you can map those back here in Wireshark. TCP.flags.syn equals 1 shows you new TCP connection attempts, which is amazing for spotting network scans. And TCP.flags.reset equals 1 highlights connection resets, a huge clue if connections keep failing or if someone is actively blocking your traffic. Ultimately, whether you're troubleshooting a broken corporate network or stepping into the shoes of an ethical hacker, understanding this architecture is your biggest asset. You simply cannot defend a network if you cannot see its layers. The OSI and TCP/IP models aren't just textbook theory. They're the literal blueprint of our digital reality. So my question to you is, now that you know how the matrix works, what network layer are you going to inspect first? Thank you for joining me on this explainer and keep exploring.